All right, the last question here is to check for the shear at section LL based on the value that we calculated on E. So to check for shear over here, you can open my formula sheet and then look for the check for RC beam shear over here. All right, step number 1 is to calculate for VC. And VC is the shear of concrete, and Vs is the shear of steel. Vc will equal to 2 multiplied by lambda, and lambda over here you can see that on the step 1 and step 2 of cracking. So if you go up here, you can see that lambda will equal to 1 for normal weight concrete, 0.85 for lightweight concrete, and 0.75 for all lightweight concrete. Okay, and then you have FC that we discussed previously. We have B that is the width of the beam, and D is also the distance that we discussed previously. So now we have step 1. We have VC equal to, that one is long, 2 multiplied by lambda. Maybe I just copy the whole thing. Copy the whole thing here. 2 multiplied by lambda multiplied by square root. Let's put the square here. Where is it? Okay, here. Square root of FC prime multiplied by B multiplied by D. So I'm gonna have lambda. First of all, let's check here. So we have this one is a normal weight concrete. So lambda will equal to 1. Let me clean this one a little bit so we can see that easier. So lambda here will equal to 1. And FC we calculate previously, that is 4,000 psi. For B, that one is 12 inches. 12 inches psi. And you have here is D is 18 inches for both section GG and section LL. We need to check for section LL, so let UD at 18 inches. 18 inches. And because you can put everything in the calculation, I forgot to add one thing over here. The desired shear force over here, finally shear force, the final unit of this one will equal to pound. I forgot that. You can make a note by yourself that this one will equal to pound. 2 multiplied to square root of 4,000 multiplied by 12 multiplied by 18. So I have this one at 27,322 pound. Okay. Step 2. Now step 2, let's go back here. Step 2 is to calculate the desired yield stress of the steel. And we calculated previously the desired yield stress of the steel is 65,000 psi. Step 3, we have the desired shear force of the steel that will equal to Vs equal to AV multiplied by FD multiplied by D divided by S. So let's put it here. let me put that into formula here. Divide by S. Divide by S. All right. So we just plug in. So we have AV. What is AV? So if you look up here, we have AV is the area of the stirrup, area of the side stirrup. So you see over here, we use stirrup number 3. We use stirrup number 3. So if you go to the reference stirrup number 3, we have the area is 0.11. So we have here is 0.11 multiplied by Fy 65,000 psi. This one in square. Multiplied by D. D over here is D over here we just calculate previously is 18 inches. And S, what is S? If you check here, you can see that S is the stirrup spacing. Stirrup spacing. So if you go up here, you can see that the spacing of the stirrup is number 3 at 6 inches on center. At 6 inches on center. So S will be 6 inches. 6 inches over here. So you're gonna have 0.11 multiplied by 65,000 multiplied by 18 divided by 6. So you have this one is 21,450 pounds. Okay. All right. Step 4. Step 4. If you go down here, you can see that step 4 is to calculate the Vn. Vn will equal to Vc plus Vs. Vc is the one we calculate on step 1. Vs is the one we calculate on step 3. And then we add them together. That will be the desired shear force for combining both concrete and steel. So we have Vn we equal to Vc plus Vs. So we have Vc this plus Vs is this one. So we have the total 27,30022 plus 21,450. I have 4A772 pound. Okay. Now step 5. Step 5 to find the Vmax. The Vmax is the one that we already calculated on question E. So we can just reuse that one. Vmax we equal to this. And then step 6. Step 6 is to check it. Let me move it here so we can have more space. Step 6 is to check for bending. If design larger than required, then it's okay. Required design will equal to 0.75 multiplied by Vn, and Vmax multiplied by FOS is the required. So we have design equal to 0.75 multiplied by Vn over here, and required we equal to Vmax multiplied by FOS. Let me put Vn here. So we have this multiplied by FOS is 1.5. So we have 0.75 multiplied by 4A772. It will equal to 36,579 pound. And this one we equal to 3900 multiplied by 1.5, 58,500 pound. So we have the design is smaller than the required over here. So which means that the shear check is not okay. So we will, this one will fail. Okay. So how can we improve that one? If the shear check is not okay, what can we do to improve the situation? So to improve the shear design, what we can do is that we can increase the S over here, or we can decrease the S over here. When the S decrease, which means the spacing decrease, then VS will decrease. VS decrease is will VN will decrease. And when VN will decrease, the design value over here, it will decrease as well. This design, oh sorry, when the S decrease, the VS will increase. VS increase, then VN will increase. The VN will increase, which means the design will increase as well. Okay. So one thing we can do is that we can reduce the stirrup spacing. So which means actually is to add more stirrup. The second thing you can do is that you can increase the size of the stirrup over here. When you increase the size of the stirrup, which means you increase AV. When AV increase, VS will increase, and the whole thing here will increase. That result in the desired value will increase as well. So you can use a bigger stirrup bar. For example, bar number 3, I will change that maybe to bar number 4 or bar number 5, like that. Okay. Beyond that, you can also increase the strength of the cement over the concrete over here. Instead of using 4,000 psi, you can use like 4,500 psi. That will improve as well. However, the easiest way to improve the stirrup is to reduce the stirrups, increase the to improve the shear design is to reduce the stirrup spacing, which means we add more stirrup or use a bigger stirrup bar. For example, instead of use bar number 3, we use bar number 4 or bar number 5. Okay.